In this massive race to build the most powerful AI, all the headlines are about one thing: size. More parameters, more data, more computing power. But behind this whole horsepower race, there's a hidden story, a really crucial economic reality that's changing the entire game. So today, we're going to explain why in the world of AI, bigger isn't always better.
So what's the best AI model in the world? It's a question pretty much everyone is asking. And if you just follow the news, you'd think the answer is simple, right? It's got to be the latest, biggest, baddest model from one of the big labs. Well, what if I told you that for most real-world jobs, that is completely the wrong way to think about it?
Yeah, there's this myth out there that capability is directly tied to scale, that a model with 1 trillion parameters is just inherently better than one with, say, 10 billion. And look, it's an easy assumption to make, but it totally overlooks a critical and very expensive piece of the puzzle. So let's dive into this AI horsepower race. For the last few years, the AI world has been absolutely locked in this competition. Every few months, boom, a new model drops. It's bigger, it's more complex than the last one, and it's claiming to be the new state-of-the-art. And a perfect example of this is Kimi K2 from Moonshot AI. This thing is a massive open-source model. It's built for super complex reasoning in these things called agentic tasks, and it's going head-to-head with the best of the best from giants like OpenAI and Anthropic. I mean, it is an incredible piece of engineering.
But here's where that scale becomes very, very real. Just to run a compressed version of Kimi K2, and I mean a quantized 1.8-bit version, you need a machine with a combined 247 gigabytes of RAM and VRAM. Just to put that in perspective, a really high-end laptop might have 32 gigs. We're talking about serious server-grade hardware just to get the thing to turn on. And believe me, that has a cost.
And this is exactly where we find the hidden price tag. It's not about how well a model scores on some academic benchmark. It's about what it costs to actually use it to do something useful. Welcome to the world of AI inference economics.
Okay, so let's make this real. A recent analysis put Kimi K2 up against a comparable model, Claude Sonnet 4. They had them do a series of real-world coding tasks. Now, both are super powerful, but their economics, well, they tell two very, very different stories. All right, so to get this set of coding tasks done, running it on Claude Sonnet 4 cost about $5. It generated a massive 300,000 tokens of back-and-forth conversation to get the job done. That's kind of the price you pay for a top-tier closed model. Now, here's the kicker. For the exact same tasks, using almost the exact same number of tokens, Kimi K2 cost just 53 cents. Let that sink in. That is nearly 10 times cheaper. All of a sudden, that question, which is better, gets a whole lot more complicated, doesn't it? This whole trade-off is so fundamental that researchers actually gave it a name: the impossible trinity. See, you've got three things you want: the best possible model quality, the fastest inference performance, and the lowest economic cost. The hard truth is, in the real world, you just can't have it all. You can't maximize all three at once. You have to make a choice. And this chart illustrates that choice brilliantly. What you're seeing here are AI models plotted by their quality versus their inference cost. So the big question is, where do you want to be? Well, you want to be up here in that top left corner: high quality, low cost. This is what's called the cost-effectiveness frontier. Any of those models down and to the right, sure, they might score well on a benchmark, but they're just not economically smart for large-scale use.
Now, all this economic pressure is forcing a really fascinating shift in the industry. I mean, if just scaling up gets exponentially more expensive, what's the alternative? The answer is to build smarter, not just bigger. It's a strategy of, well, brains over brawn.
And this is exactly where small language models, or SLMs, come into play. We're talking about models with under 10 billion parameters, sometimes way, way less, that are designed from the ground up to be efficient and specialized, instead of trying to be some giant one-size-fits-all solution. But here's the secret sauce. Their real power doesn't just come from being smaller. It comes from being part of a smarter system, what you might call an agentic framework that orchestrates the model's abilities in a much more intelligent way. These frameworks work kind of like a project manager. Take this one, the Nanobio Agent Framework. It's designed for complex genomics questions. So instead of just throwing one giant prompt at a single huge model, it breaks the problem down. It classifies the task, figures out a plan, and then uses these small, specialized tools, some of which are tiny AIs themselves, to execute each step, like querying a database or parsing a document. And the results are just stunning. This graph shows you the performance of different models on that genomics task. See that bottom line? That's just direct prompting. Doesn't do very well. The middle line is a bit more advanced, but look at that top green line. Those are small models, between 3 and 10 billion parameters, but they're using that smart agent framework, and they are consistently hitting 85 to 97% accuracy, absolutely crushing much larger models that are just trying to brute force an answer.
This all leads to a powerful new philosophy in AI development, and it's best summed up by the researchers themselves. The key to effective AI deployment lies not in model size, but in architectural innovation. I mean, that's a complete paradigm shift. So, how should we be thinking about comparing models now? It's clearly not just about benchmark scores anymore. We have to bring economics and efficiency right into the center of the picture.
Let's go back to our production frontier chart one more time. Thinking like an AI economist means you're looking for value, not just raw power. The best model for your job isn't the biggest bubble, it's the bubble that's pushed furthest into that top left corner. Efficiency, that's the new benchmark for excellence.
So, what does this all mean for the future of AI? Well, it means the landscape is about to get way more diverse and interesting from just a simple battle of titans. So let's quickly recap the big points. First off, bigger isn't always better, because actually using these things, AI inference, is expensive. That means the real race is now about economic efficiency. Second, as we just saw, small models with smart architectures can totally outperform the giants on specialized jobs. And finally, this all points to a future that's this rich ecosystem. You'll have giant generalist models working right alongside an army of hyper-efficient specialists.
And that leaves us with a pretty fascinating thought. For all the talk of trillion-parameter models, the next truly revolutionary leap in AI, it might not come from a bigger model at all. It might come from one that's smarter, more elegant, and radically more efficient. The only question is, which future are we going to choose to build?